Hi students, I am Praveen Sebastian Paul. In this lecture we are discussing the example number 5 for the Boolean function simplification using 3 variable K-map for SOP equations. So as we discussed in the previous lectures, the SOP can be reduced using K-map by applying different reduction rules. Those rules are detailed in the lecture number 71, and those rules include pair reduction, chord reduction, octet reduction, map rolling reduction rules, overlapping group and redundant group rules. So my dear students, in the last 4 set of lectures we had discussed different examples for SOP reduction using 3 variable K-maps. And my dear students, in this lecture we are discussing another example. Our question is, simplify the Boolean function x dash y plus y dash z plus x dash z dash using 3 variable K-maps. So my dear students, here we got different variables itself. The min terms are not yet represented in this question. So we have to identify the total number of variables in this given question. So we can see x, y and z. That means we are dealing with 3 variable SOPs. So in the case of an SOP, if we are dealing with 3 variable, each and every individual term must have all these 3 variable. That is, here the 3 individual terms are x dash y is the first term, y dash z is the second term, and x dash z dash is the third term. The first term x dash y is missing the term z, y dash z, the second term is missing x, and the third term x dash z dash is missing the term y. Thus, in the next step, we have to expand these set of function by adding the missing term. For that, x dash y should be ORed with z plus z dash. By adding or by ORing these terms, there will not occur any change, since z plus z dash simply means 0 plus 1, which is equal to 1, and 1 is ANDed with x dash y means x dash y itself. So net effectively there is no change. Thus the function can be expanded as x dash y into z plus z dash plus y dash z into x plus x dash plus x dash z dash into y plus y dash. While expanding this, the function becomes x dash yz plus x dash yz dash plus x y dash z plus x dash y dash z plus x dash yz dash plus x dash y dash z dash. Here in this form, x dash yz dash is repeating twice. Thus, we can rewrite it into one time only. So the function can be reduced into x dash yz plus x dash yz dash plus x y dash z plus x dash y dash z plus x dash y dash z dash. While converting this into the minterm representation, x dash yz can be represented as 0, 1, 1. X dash yz dash can be represented as 0, 1, 0. X y dash z can be represented as 1, 0, 1. X dash y dash z can be represented as 0, 0, 1. And finally x dash y dash z dash can be represented as 0, 0, 0. These can be represented in the K-map as follows. Since we are dealing with a 3 variable K-map, the total number of cells available in the K-map should be 2 raised to 3. So this 3 means the total number of variable. Thus the total number of cells is equal to 2 raised to 3, which is equal to 8 cell K-map we are using. In this 8 cell K-map representation, we can see 2 different rows and 4 different columns. The rows represent the variable x and columns represent the variable y and z. And in each and every cell we can see a suffix which represents the min terms. That is, the suffix in a cell 0 means we can write the min term 0, m0 in that particular cell. The suffix 7 means we can write the min term m7 in that cell. That simply means that 0, 0, 0 is the minterm m0, and that minterm m0 can be represented in the column 0. 0, 0, 1 is the minterm m1, which is represented in the column 1. So we can write 1 in the column number 1. And 0, 1, 0 is the minterm m2. Thus, the digit 1 is represented in the column 2. 0, 1, 1 means the minterm m3. Thus, the third column, column 3, is represented with 1. And finally, 1, 0, 1 is minterm m5. Thus, 1 is represented in the column number 5. So, the rest of the columns should be denoted or represented or marked with zeros. Thus, the K-map will become like this. In the next step, what we have to do is reduce this K-map using different rules. So, starting from the code, that is the first row, the row with the cell 0, 1, 3, 2, and this is represented in the red rectangular representation. The second reduction applied to this K-map is the pair reduction rule with the cells 1 and 5. Here we can see the cell number 1 is overlapped in both these, which is not a problem in the K-map reduction. So now we have to reduce the variables. For that, let us consider the first cell, that is a code. While considering the code, we can see that the code consists of the cells 0, 1, 3 and 2. Here it is lying in the row number 1, and the variable in that row is x with the value 0. That means the value x is equal to 0 is not changing in this set, while the values of y and z are changing while we are moving from left to right in each cell. Thus, the unchanged values are taken into the final set, which simply means the simplified or reduced form of first code is x is equal to 0, that is x dash. While taking the second set, that is the first pair, which is represented in the yellow rectangle, the pair lies in 2 rows. Thus, the value of x is changing from 0 to 1 when we are traveling from row 1 to row 2. Thus, x is not considering, and it lies in the column number 2, and therefore the value of y and z is unchanged. Here the value of y z is 0 and 1. The value of y is 0 and value of z is 1, which means the first pair's reduced value is y dash z. Thus, we can conclude that the SOP for this given expression is x dash plus y dash z. That is, the function x dash y plus y dash z plus x dash z can be reduced into x dash plus y dash z. So my dear students, hope you had understood this example. So my dear students, kindly go through this assignment question. The question is, simplify the Boolean function f of def is equal to sigma 1, 2, 3, 5, 6, 7 using 3 variable K-map. So my dear students, in the upcoming lecture we will discuss the last example for 3 variable K-map solution.